So let's look at 24 on page 529. No, it's still in 528. Very good. 24 tangent. Very nice pick. Plus the square root of 3 equals 0. Awesome pick. I would have chosen something, not exactly this one, but I would have chosen similar situation or type of problem. Good. So I see tangent. So then on the side I write that cosine theta over 4 cannot equal 0. I'm going to erase that thing, whatever that is, up there. So obviously cosine theta over 4, when I'm done and I find the solutions, I'll go back and make sure that cosine of theta divided by 4 is not 0, right? Because this is the denominator of a rational function.
Yeah, right.
Perfect. What will be my first step here then?
Sine theta over 4.
Nope. I'm going to write tangent theta over 4 equals negative the square root of 3.
Oh.
Then I'm going to ask myself, where is tangent negative? And the answer would be
Second and fourth.
second and fourth. Awesome. Very good. Now, the square root of 3, I know. And I only have two options. One option is, let me write the two options. One option is 1/2 over the square root of 3 over 2. And the other, for the small angle. And the other one is the square root of 3 over 2 over 1/2. When I flip, which one will I get? I know, not negative, but will I get the square root of 3?
Second.
The second one, right? Because I flip and I get the square root of 3. What is this angle?
Sine.
Which angle?
66.
Yes, of course, or pi over 3.
Yeah.
Very good. So then I know 60 degrees. The reference angle must be 60 degrees or pi over 3, as well as this reference angle must be pi over 3. So then I know what theta over 4 should equal to. And there are two options. What is the first option? Obviously, pi minus pi over 3,
Right.
which is 1 integer minus 1/3. Yes, right? So from pi, I subtract pi over 3. 3 over 3 minus pi over 3 is 2 over 3, correct?
Mhm.
And plus what?
Okay.
Very good.
Yeah, pi equals 10.
Very good. On the side, I write k integer. You don't have to write it more than once per problem, but you have to write it. Very good. I'm not done. I want the second angle, please. The second angle is 2 pi short pi over 3, right? So 2 pi minus pi over 3. 3 times 2 is 6, yes. 5 pi over 3 plus pi k. This is awesome, but this is not what I'm looking for. What am I looking for? This is good.
Theta, 15.
Yes. So, but I had no choice. I had to solve for the argument inside tangent first. But now I want to find theta. What should I do to both sides to find theta?
5 by 5 by 4.
Why divide,
Or,
right?
yeah. Because they just want to divide by 4.
Multiply. If I want to divide, if I want to get rid of something in the denominator, yes. So theta equals 8 pi over 3 plus 4 pi k. And theta equals 20 pi over 3 plus 4 pi k. I would like to look at a problem from 39 through 42. Any questions on this? So we applied the exact same principles, but this time I had to apply the principles for theta over 4. And once I changed the equation that was trig equation into a linear equation in theta, I had to multiply both sides by 4. Now, theta is this, or theta over 4 is this. I know that cosine 2 pi over 3 and cosine 5 pi over 3 is not 0. So theta over 4 is 2 pi over 3. That's not 0. 5 pi over 3 is not 0. I have to check. Is this okay? Perfect. So let's choose now from 39 through 42. And as I said, we can go on forever. You said 40?
Yeah.
Very good. So let's look at 40 and then move on to chapter 4, unless you want more. Cosine theta, cosine 2 theta, plus sine theta, sine 2 theta, and they say this is 1/2. We're asked to use formulas, identities, and then find all solutions in the interval 0 to 2 pi. They don't want us to go back or to go around the unit circle and find all of them. They only want us all the solutions in one complete rotation, in 0 to 2 pi. Good. So I look at the left-hand side. I look to the left-hand side and I see what? I see something that rings a bell. Cosine, cosine, plus sine, sine. And that is an identity. And if it's cosine, cosine, sine, sine, must be cosine. And now in parentheses of what? Yes?
Theta plus 2 theta.
If this is, that's the wicked one. Yes. Yes. So it's plus here, so it's minus here.
Yeah.
Okay, so theta minus 2 theta. Perfect. Now, how much is theta minus 2 theta? Good. So cosine of negative theta equals 1/2. When I see a negative angle inside a trig function, I will always ask myself, is this trig function odd or even? If it's odd, cosine negative theta will be negative cosine theta, and I make my life easier. If it's even, then cosine negative theta will be cosine theta, and my life is even easier. It's even function. So this is the same thing with, you don't have to erase, I'm just making a point, is this. Why not? If it's the same, if the function is even, why not use the positive angle? So now I am asked to find theta only in one complete rotation, from 0 to 2 pi. How many angles will I find specifically? Not infinitely many, but specifically?
2.
One in which quadrant and one in which quadrant?
First and fourth.
First and fourth. So here it is. This is 1. This is half. This is half. So I'm looking at this angle, and I'm interested in this angle. I know which angle has cosine 1/2, and it's not the tiny one, because sine is 1/2 for the tiny one. So then I know which reference angle. Pi over 3. So these both are pi over 3. So then theta has two options. Pi over 3, and I can't say anything else, because that's how they want the answer. And the other option is theta equals this angle from here, here, which is 2 pi, pi over 3, backwards. Yes, 2 pi minus pi over 3. 2 times 3 is 6, minus 1, 5. Any questions? Well, this is the end of trig, unless you want me to go back to anything. Say it again?
Let's leave it forever.
So anything else you want me to go back to? Do we need more examples from trig equations? Or we put trig to rest and we go back to chapter 4? Once? Twice? Okay, sold. So please, as soon as possible, after you take this test, work on any problem, as many as you can, and check the answer in the back and say, I'm not sure about this, or I'm not sure about that, or, okay?
Yeah.
Okay, so now we're going to look at chapter 4. Chapter 4. We did in class a problem from, I would say, 95% of all those problems that I showed you. If there is one that we didn't, let's do it together in class, if you have any difficulties with it, okay? Okay. Chapter 4 deals with two functions that are widely used in real-life situations, in models. Exponential functions and log. Exponential and logarithmic functions. We start with the exponential. We're going to look at the graph. We're going to understand the graph like we did with rational functions, bless you, polynomial functions, etc. We're going to look at the logarithmic function. We're going to learn how it's graphed. We're going to learn about its properties. They are absolutely unique properties that you will never encounter in any other function, but in logarithmic function. And then we're going to look at equations, exponential equations and logarithmic equations, and then applications. So one more time, we're going to analyze the graph of exponential, the graph of log. Then we're going to look at equations that are exponential and equations that are log. And then we're going to apply these functions in applications. Okay. So let's start with the exponential function 4.1. Here's a question for you. What function is this?
Absolutely.
Why?
Absolutely.
Because it has an absolute value. What function is this? Why? So why do you think, I haven't even showed you this function yet, but what do you think it's called exponential? Of course. Furthermore, the variable is the exponent, not the base. So an exponential function looks like this. A base that is a number, and I'll explain this in a moment, and x is the variable, and x is the exponent. So this is the exponential function. Exponential function. Okay. Let's talk about this piece first, which is the base. Then we're going to talk about this, which is the power. We prefer to say exponent. Before we talk about the base, I have a question for you, or several. Can anyone give us the answer for 0 to the 4th power?
0.
Can anyone give us the answer for 1 to the 3rd?
1.
And can anyone give us the answer for negative 2 to the 4th?
16.
So they're all possible, right? I can raise 0 to a power like that. I can raise 1 to a power, and I can raise a negative number to a power. All these are not allowed for exponentials. So the base of the exponential function, which is a, can be one or the other. Strictly greater than 1, never 1. Or the other option is a tiny positive number between 0 and 1, not 0, not 1. Now the reason is why. We just showed that we can raise 0 to any power. We just showed that we can raise 1 to a power. And we just showed that we can raise negative numbers to different powers. How come that the base of the exponential function must be positive, not 0, and not 1? Either greater than 1 or tiny between 0 and 1. No. So the reason is its inverse function will not exist. That's the problem. Remember, we did this before with sine. We said, okay, sine is not 1 to 1. How can I find its inverse? How can it have an inverse? And we said, okay, we know how to handle that. And we said, it's defined here. And we're done. The same thing here. The inverse function of the exponential function will not exist because the bases must be the same. So there is no base 1 for the inverse function. There is no base 0, and there is no negative base. It will not exist. So that's the only reason. Like we did with sine and cosine and tangent, we truncated the domain. We said this is it, which was false. Here it's true, actually. We can use these bases other than greater than 1, not 0, and never negative, because the inverse function will not exist. Okay. Because there are two options for the base, the function will have two different shapes. Have we encountered that before? Yeah. For example, a quadratic function with a positive leading coefficient has a minimum. A quadratic function with a negative leading coefficient has a maximum. Yeah. So there are two different shapes. So let's look at two different examples. Give me a base that is a number greater than 1. And don't say 1.75 because it's going to be difficult to handle. Not impossible. 2. It's a very simple example. And give me another one with a base between 0 and 1. 0.5 is good, which is 1/2, let's say even 1/3, it doesn't matter. To the x. Is it clear that this will be from the first shape?
Yes.
Is it clear that this will be from the second shape?
Yes.
Because 1/3 is between 0 and 1? Okay. Now, before we graph both shapes, I want to go back to the exponent. Now we identify the base. We know that the base is restricted. It cannot be just anything we can think of. It has to be definitely positive and not 0, not 1. Now let's look at the exponent. Because the exponent is the variable in the function, when I talk about the exponent, I talk about what? Indirectly or even directly. When I talk about the x of a function, I talk about the of the function. What is connected to x? Domain, right? Right? Good. So when I talk about x as the variable in the problem, and which is the exponent for the exponential function, I'm asking now, what is the domain? What can x be? So, in other words, I'm asking you here, can I raise 2 to -5? Yeah, it's 1 over 2 to the 5th power.
Yeah.
Can I raise x to 0?
Yeah.
Can I raise x to 15?
Yeah.
So then, will I consider exponential function a friendly function or not? Friendly, which means the domain of all exponential functions are like the domain of all polynomial functions. That's it. So the domain of any exponential is all real numbers. Friendly, like polynomial functions. Awesome. Good. So then when I start my chart, I will write -∞ to infinity for any exponential function, like I do for any polynomial. I will pick some x values. Well, let's say -2, -1, 0, 1, and 2. Let's plug in -2 here in the function so I can find the y value. 2 raised to -2. 2 raised to -2 is 1 over 2 squared, which is 1 over 4. Very good. Good. Let's plug in the function -1. Very good. Let's plug in the function 0. Exactly. Any number raised to 0 is 1, except 0. You have to wait till Calc 1 for that. 0 raised to 0 is not 1. But any number that is not 0 raised to 0 is 1. Okay, in parentheses, I have to write this. A not equal 0. Good, so please plug in 1 and tell me the answer. Okay, plug in 2 and give me the answer. Good. We have never done this with the previous functions. Okay, but for this one, this works. What? Hold on. I want the end behavior. We have never done this. The procedure that I'm using right now, it's not something we want to use for other functions. Okay, I want to go this way. 1 over 4, 1 over 2, 1, 2, 4, 8, 16, 32, 64, 128, 10,000. Where am I going? Thank you. I want to go this way now. 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32. I have a cake and I want to. Indeed, I'm approaching 0. I cut it and I cut it and I cut it, and by the time, okay. This is very clear. But what does this mean? From our experience with rational functions, when x approaches either negative infinity or infinity, if the function values approach a number, not infinity, but then approach a number, what is that? Thank you. So then y equals 0, we have never seen this before. Horizontal asymptote at negative infinity only. We have never seen this before. All our rational functions had horizontal asymptote, the same one, and horizontal asymptote at both ends. This one does not. Okay, so we are ready to graph it. So let me remind you, we are graphing an exponential function with a base greater than 1. And we have a lot to learn here. When I graph a function with asymptotes, what do I have to graph first? Yes. Well, it's an overkill, right? Because it's already there. It's y equals 0. So in the first ordered pair that I would plot, which is not easy, right? It's 1/4. At -2, I'm going to take this big unit and I'm going to say negative, so 1/4 is here. At -1 is 1/2. At 0 is 1. At 1 is 2. And so on and so forth. This is the graph of 2 to the x. This is the fastest growth that we have seen in any of the functions that we looked at. You mean this one? The horizontal asymptote?
No, I'm just talking about where it crosses. Were those ordered pairs? You just pick those?
I just pick the x
Yeah,
values.
yeah, X value.
Yes, and I determine the y values.
Yeah, yeah.
Yes.
So, like, you just.
Yes, because I didn't want to go too far away from 0. Because it's going to be more difficult to graph. I'm not going to plot something here.
600.
Right. Very good. Okay. So here's what I can say to you when I look at this function. And if we need to write these down, we will. If you ask me, what do you see? Oh, I'll say this. This is a function that is defined on all real numbers, has a range from 0 to infinity. It's increasing on all its domain. It's 1 to 1, which means it has an inverse function by the horizontal line test. It does not cross the x-axis. There is no x-intercept. There is a y-intercept at 0, 1. And it appears to have a very fast growth, exponential growth. Now, I have some students who in the middle of the semester ask me, hey, professor, I know I have an F so far. Can I still get an A in the class or pass the class? And I say yes. If your grade from now on follows an exponential function with a base greater than 1, yes. I said, what? I said, I'll show you. So, because it's 1 to 1, I'm going to go ahead and graph its inverse function. I need a couple of, maybe 3 ordered pairs, so I can graph the inverse function, please. Of course, 1, 0. It's a reflection of this point with respect to y equals x. Awesome. 2, 1. Okay, let's also go this way. So let's say 1/2 negative 1. That will be the inverse function. What can you say about the inverse function? Here's what I would say about the inverse function. It's also increasing like the original function. It's also definitely 1 to 1. However, it's not a friendly function. It has a vertical asymptote. Where is the vertical asymptote? Exactly. Because this one has a horizontal asymptote y equals 0, of course, when I transpose the graph over y equals x, the inverse function will have a vertical asymptote at x equals 0. Okay, now let's go back because I said it quickly. So let's write the properties of the exponential function with a base greater than 1. Okay, properties. For 2 to the x. I'm going to say the exponential function is defined on all real numbers, and its range is
Zero at the parentheses.
very good. That's the first thing, domain and range. Number 2, the function is increasing on all its domain. Number 3, y equals 0, horizontal asymptote at negative infinity only. 4, no x-intercept. Number 5, y-intercept 0, 1. 6, what is this? It has F inverse. I should have written it here because it is 1 to 1 by the horizontal line test, comma, by the horizontal line test. A lot. Yes?
K, let's do, yeah, 2, number 2.
F is increasing.
Okay.
F is always increasing on all its domain. Horizontal asymptote is y equals 0 at negative infinity only. No x-intercept, y-intercept is 0, 1, and it has F inverse because it is 1-to-1 by the horizontal line test. And we already graphed its inverse. Okay.
What's number 6 again?
Yeah, I started with the, it has F inverse because it is 1-to-1. Sorry about that. No excuse, but because I stand, my handwriting is not the best. I apologize for that. Good. So now I'm going to say, before we look at the second shape, I'm going to